Okay, I think it's good time to start. Good afternoon, everyone. Welcome to the first talk of this section. I'm honored to introduce the first speaker, Professor Richard Samworth from the University of Cambridge. Today he will talk nonparametric inference under shape constraints, past, present, and future. Let's welcome Professor Richard Samworth.
Okay, good afternoon, everyone. Hope you can hear me. It's a great pleasure to be here, my second time to Beijing, and really having a good time here. So nice to see everyone here. All right, so I'm going to be speaking about an area that I find particularly fascinating within modern statistics. I'll try and say something about the history of this area and how it came into being, the sorts of problems that I find interesting now, and I'll try and conclude with a few open problems in case there are people who are looking for problems that they want to solve. Okay, so in statistics, we like to ask the question, what distribution did my data come from? Right? Unfortunately, there are many different ways in which we can ask this question, which is lucky because it keeps people like me gainfully employed. But this is perhaps one of the most simple ones. Let's suppose I have a random sample of data from a distribution on R to D, and I ask, how should I estimate the density F0? By the way, because this is a kind of general maths kind of conference, I'm going to certainly start at really a very basic level that I hope will be very comfortable for people who don't consider themselves to be statisticians here. I'm sorry if this is sort of teaching grandmothers to suck eggs for the experts here. Okay, so the sort of first type of method that we teach in elementary courses in statistics is based on parametric models. So here's an example of 200 data points that I drew from a particular gamma distribution. The gamma density is plotted there. And then what I can do is I can just estimate the parameters using, for instance, a maximum likelihood estimator. And even with a relatively small number of observations, I can get really quite a good estimate here. Okay. So it seems like, what's the issue? Well, so I run something called the Statistic Clinic in Cambridge. So that means once a fortnight, anyone in the university can come and get help with their statistical problems. And I have to say, it's pretty unusual for a client to come along and say, I know my data came from a gamma density. Would you mind just estimating the parameters for me, right? So more typically, you just get the data. So what happens if things go wrong and you specify the wrong type of parametric model? Let's say you thought these came from a normal distribution and you use the same method, you use maximum likelihood estimation. Well, then this is the density that you end up with. It's a disaster, right? It's not doing a good job at all of capturing the true distribution. And of course, the issue here is here that we've restricted to a very small, low-dimensional parametric model a priori here. So if we were to try to extend the idea of maximum likelihood to wider classes, then the first observation is, well, how should we define the likelihood in this case? When we talk about the likelihood of a particular parameter value in a parametric model, what we're really talking about is the likelihood of the distribution with that parameter value. So that tells us how we should define it in general. For a general density F, we should define the likelihood to be the product of the density at the observation. So we're trying to make the density at the observations high, but without any further constraints, then we run into something called the Dirac catastrophe. So this is a picture of the Dirac catastrophe. The likelihood is unbounded. I can make it as big as I like by kind of approximating spikes on each of my true data points, each of the observations that I see. I could make these spikes taller and taller. I have to make them thinner so that the density still integrates to 1, but that's no problem. I can do that. So what's really going wrong there? Well, I don't really believe that all the mass of the true distribution is so tightly concentrated around the particular observations that I see. So what people have done for perhaps 75 years or so now is often to work with non-parametric density estimation methods, and perhaps the most common and simplest of these is perhaps not the simplest, a kernel density estimator. This is a sort of slight generalization of a histogram. So the idea is, again, very simple. We take our observations, and here we just have 5 observations for illustration on the real line. We give each of our n observations mass 1 over n, and we spread it out with these little kernels that are centered on each one of the observations, and then the final density estimate we get by just adding up the contributions from each of the individual kernels. Okay? So that's a very simple method, and what's kind of interesting, and the sort of thing that I would teach to my master's students, is that actually the shape of the kernel, whether you choose it to be a Gaussian density or a uniform density or something, doesn't actually matter too much. But what's really crucial is the scaling of this kernel. So the kind of, you could think of it as the standard deviation of the kernel. So here's a picture where we have a true distribution, which is this bimodal, a mixture of Gaussian distributions as it happens. And in the top right, you see what happens if we choose this scaling, this bandwidth to be too small, the standard deviation to be too small. You end up with these sort of spiky kernels on each observation, and when you add them up, you get this rather wiggly density estimate. Okay? In the bottom right, you see what happens if you choose it to be too big. You're rather over-smoothing the data, and you might actually wash out, for instance, the bimodality, which is presumably going to be a feature of this density that you'd be particularly interested in. And so the aim of the game is to end up with something of a Goldilocks, somewhere in the middle choice of bandwidth, where you're getting a sort of good amount of smoothing here. And really, you can think of this as what I call a bias variance trade-off. In the top right situation, where you're choosing the bandwidth too small, you've got a low bias and a high variance. And in the bottom right, you've got a high bias and a low variance. And this is getting something approaching a good trade-off. But choosing this smoothing parameter is the kind of bane of every statistician's life. And you can imagine that in d dimensions, it's a much more complicated problem than in one dimension, both in theory and in practice. So the starting point for the kind of area that I want to introduce is we're looking to try to get the best of both worlds. We're looking to try to have this generality of the non-parametric model, the flexibility to be able to fit much more general classes of densities, but also to have our cake and eat it, and be able to have the sort of fully automatic nature of the maximum likelihood estimator, where you don't have these difficult smoothing parameters to choose. And so the first contribution in this general direction was made by a Swedish statistician called Ulf Grenander, and this dates back to the 1950s, 1956 to be precise. And he thought about the following quite simple problem. So let's suppose that I have some non-negative random variables. I can think of them as IID for now. And Grenander proved that even though the class of right continuous decreasing densities on the non-negative half-line is an infinite dimensional class of distributions, there nevertheless exists a unique non-parametric maximum likelihood estimator. So all I've done here is I've taken the logarithm of the likelihood function as I defined it before, and I divided by n. That doesn't change whether or not there exists a maximizer, right? So this is the unique non-parametric maximum likelihood estimator. And intriguingly, he actually characterized what this non-parametric maximum likelihood estimator looked like. It's the left derivative of the least concave majorant of the empirical distribution function. So that might sound like a bit of a mouthful. Let's look at what it looks like in a picture. So here we have a situation where we have 30 observations that come from an exponential 1 density. The exponential 1 distribution function is plotted in blue there, and you can see the empirical distribution function of the data. And so on the distribution function scale, what we're doing is we're computing its least concave majorant. This is a piecewise affine function, and you can see the way that it sort of fits together to form the least concave majorant. And then on the density scale, I have to take its left derivative to end up with this piecewise constant density estimator. Okay, and you can see the way that this is estimating this blue curve. Of course, I've only got 30 observations here, so there's a limit to how well I can do in terms of estimating the true density. Okay, this is, I think, a rather beautiful estimator. Then the question might be, what can we say about how good an estimator this is? So here's a very simple, but I think rather beautiful result due to Al Marshall from 1970. It says, let's let black ball bold Gn denote the empirical distribution function. and g hat n is going to denote the Grenander distribution function. So that is this piecewise affine function that I've got in black here. And it says that for any concave function g, so in particular, if I were to draw my data from a decreasing density g0, then its distribution function would be concave. And it's saying that the Grenander distribution function is closer, or at least as close, in the subnorm compared with the empirical distribution function. So we think of the empirical distribution function as it's a really good way of estimating a distribution, and I find this a very intriguing result here. And it's so simple. There's no kind of nasty constant that is hidden here or anything like that. It's so simple. I'm even going to prove it for you. This is a risk, but I'm going to prove it for you now, because the proof is only 4 lines long, and one of the lines only has a few characters as well. How does the proof go? Well, if I think about the function which maps x to g of x plus this uniform norm distance, that is a concave function plus a constant, so it's concave. And this majorizes the empirical distribution function. If I take g and I add on this uniform distance here, it majorizes the empirical distribution function. But I know that the characterization of the Grenander distribution function is that it's the least concave majorand, right? So in other words, this guy must be at most the original g of x plus this uniform distance. So that's a one-sided bound once I take the g of x over the other side, because this holds for an arbitrary x. To get the other bound, I just have to observe that g hat n does majorize the empirical distribution function, and that's at least as big as the g of x minus this uniform distance. So that's the whole proof and nothing but the proof. That's a very simple result. But nevertheless, that doesn't say necessarily everything we'd like to know about the Grenander estimator. In particular, it doesn't say something about how well the density is estimated. So this is a rather deeper and more complicated result, one I'm certainly not going to prove now, but I will try and talk about what it's saying. Okay, how should we measure study the performance of statistical procedures of density estimates? Well, first of all, we need to agree on how we're going to measure distance between the estimate and the truth. Okay? There are many ways in which you could do this, but a very natural one is to think about the total variation distance, which I can think of as half the L1 distance between the densities. Now, the issue here is that the total variation distance between a density estimate and the density is a random object. It depends on the particular realization of data that I see. I can solve that. The simplest way is to just work with the expected total variation distance. That turns this random quantity into a non-random one. But then I need to also think that it depends on what the true density is as to how good an estimate this is going to be. I mean, if there were only one density that I were considering, I should output that density and I get 0 here. That's not an interesting result, right? So a natural way to proceed is to think about a class of particular densities and then try to look at the worst case of these risk functions over the class. And having taken the worst case risk, now we've got a non-random quantity that only depends on the class, and we can try to minimize that over all estimators. So here we've taken the worst case density and we try to take the infimum over all estimators. So the particular class that we're going to consider here is this class of decreasing densities on the non-negative half line that have height h and are supported, that have length at most L, okay? And what do we see? We see upper and lower bounds on this, what we call a minimax risk, that match up to a constant factor of 10. Okay, the 10 is kind of induced by the sample size condition here. You might think that a factor of 10 is not a particularly good factor here. It's kind of a factor of life somehow as a statistician, that actually being able to get minimax bounds that match up to a universal constant is already very good, and we sort of typically think of the problem as solved in that case, and a factor of 10 is a lot better than we'd typically expect for many modern problems. Okay, what's interesting here is we're seeing that this minimax risk scales at like n to the minus a third. Okay, so I need to blow this up by a factor of n to the 1/3 to get this sort of non-degenerate quantity here. So that's slower than I would typically expect for a parametric estimator in a well-specified parametric model, where in regular parametric models I expect an n to the -1/2 convergence rate. And that is somehow reflecting the price we pay for the generality of working with this infinite dimensional class. Of course, in the parametric model, if my parametric models misspecify, I don't tend to 0 at all. So that's the kind of trade-off that we're working with here. We can also see the way that the height and the length enter into this minimax bound. So for instance, we know that the total variation distance is scale invariant, and this product of the height times the length is also going to be scale invariant. And so that's another reason why we can get this to within a universal constant, but we can see this s to the 1/3 factor appearing here. So we're kind of getting the right dependence on these quantities. A slightly unfortunate aspect of this result is that even for something simple like an exponential density, we're not saying anything about how well the Grenander estimator performs. I should have also said that the upper bound here is attained by the Grenander estimator. So in order to prove an upper bound here, I need to exhibit an estimator and say something about how well it performs. And we're talking about the Grenander estimator here that's attaining the upper bound. But this is the exponential density does not belong to any of these GHL classes, for instance. Okay. The class of decreasing densities on the non-negative half-line is a kind of nice toy case, but is a very toy case. It is very specialized, and for instance, it doesn't generalize particularly nicely to multidimensional problems. There have been generalizations of it, for instance, to convex decreasing densities, where you'd get a rate of n to the 2/5 here instead of n to the 1/3, and more generally to K monotone densities. But I want to talk about perhaps more modern shape constraints, and there has been a lot of work in this area, particularly over the last 10 to 15 years, I would say. And the constraint that I want to focus on for most of the rest of this talk is the constraint of log concavity. So we've got a very simple definition here. A density f is log concave if its logarithm is a concave function. So this definition works equally well in d dimensions as it does in one dimension. Let's try to build some intuition. We've got a lot of univariate examples of log concave densities. Of course, a Gaussian density is log concave because the logarithm of the density is a parabola. But logistic Gumbel densities, a viable density provided the shape parameter is at least 1. Gamma density provided the shape parameter is at least 1. So for instance, chi-squared densities with chi-squared n densities with n greater than or equal to 2 would be log concave. Beta densities where both parameters are greater than or equal to 1 would be log concave. You want to think of log concave densities as being unimodal densities with exponentially decaying tails. Okay? But what really makes this class particularly attractive to work with is it's got a lot of stability properties. So it's closed under marginalization. What do I mean by that? I mean, if you start with a random vector x having a log concave density, you take a subset of its components, then that's got a log concave density. It's also closed under conditioning, under convolution, so convolutions of log concave densities are log concave, and under linear transformations. And an interesting aspect is that all of these properties are shared by the class of Gaussian densities, right? So in many ways, you can think of the class of log concave densities as a very natural infinite dimensional generalization of the class of Gaussian densities. Okay, so I want to talk about how we can try to estimate densities over the class of log concave densities. So the kind of starting point for this work is a result that I proved with Lutz Dumgen and Dominic Schumacher in a paper from 2011. So I need just a little bit of notation. I'll write curly PD for the set of probability distributions on R to D that have got a finite mean, and that are genuinely d-dimensional in the sense that they're not concentrated on any hyperplane. They don't give mass 1 to any hyperplane. Now I'll let curly FD denote the set of log concave densities on R to D, and I'll insist that they're upper semi-continuous. That's not important. That's just fixing a particular version of the density, because log concave densities could only have discontinuities on the boundary of their support, and that would be a boundary of a convex set, which would have Lebesgue measure 0. And the result says that there exists a well-defined projection from this set curly PD to the class curly FD, and it's defined in this way. So psi star P is going to be the log concave density that maximizes the integral of log f dp. Okay? So this is written in slightly different notation, but this is essentially on the population level. This is saying that there's a unique maximum likelihood estimator over this log concave class. Okay? So again, this is very attractive because it's giving me a way now in d dimensions to get a fully automatic non-parametric density estimator. It's a very attractive way to proceed. Actually, if this distribution P has a density F0, not necessarily log concave, then under a mild integrability condition on F0, psi star P is finding the log concave density that's minimizing the Kullback-Leibler divergence from F0. In other words, I can think of psi star P as a projection onto the class of log concave densities, right? So the class of log concave density is certainly not a convex class. If I took a Gaussian density over here and a Gaussian density over here, and I take their mixture, that's certainly not going to be log concave, right? But nevertheless, there is a well-defined notion of a projection. This is not an obvious fact, but I think it's an interesting one. If my P is an empirical distribution of some data, then it's certainly the case that it's going to have a finite mean. It's just a sample mean. And this condition would be saying that the convex hull of the data is d-dimensional. Right? So when the convex hull of the data is d-dimensional, we're saying there exists a unique log concave maximum likelihood estimator. So let's get some intuition about what these log concave projections look like. So in green here, I've plotted a rather heavy tail density. It's a T2 density. And then in blue is its log concave projection. So this is in some sense the closest log concave density to it. Now, of course, that's got much lighter tails. It's got exponentially decaying tails. But certainly you don't really see that until you get really quite far into the tails. A T2 density's got a finite mean, which I needed, but it doesn't have a finite variance, for instance. Here's a bimodal example, a mixture of Gaussian densities. And what you can prove here is that the log concave projection exactly matches the truth up to some point, and then it's log linear, and then it exactly matches the truth in the right-hand tail. Okay? So, of course, it couldn't capture the bimodality of the density because it's got to be a log concave density, but still it's doing a reasonable job in some sense of approximating this bimodal density. Okay? So more generally, there's a significant computational question of how can I compute this log concave maximum likelihood estimator if you just give me a sample of data. So here are a few different plots of what the density estimator looks like. In this case, this is for 1,000 observations from a standard bivariate normal density. And so what you see from this plot is that there's actually a slight discontinuity on the boundary of the convex hull of the data. Outside the convex hull of the data, the density estimate is 0. And on the interior of the convex hull of the data, what you get on the log scale is the maximum of a bunch of piecewise affine functions. So maybe that's easier seen with this cartoon picture on the bottom. The idea is that to each data point, you associate a certain tent pole height. So that's going up here. And then for a certain vector of tent pole heights, the logarithm of the maximum likelihood estimator is what you get by stretching a taut tent over these tent poles. Okay? So in other words, what we've done is we've reduced this infinite dimensional optimization problem over the class of all log concave densities to a finite dimensional one, admittedly in n variables still, but a finite dimensional one where we have to optimize over the heights of the different tent poles. Okay, so then the question arises of what can we say about the behavior of this log concave maximum likelihood estimator. And this result you can think of as a kind of basic inequality. It comes from the first order stationarity condition for the log concave maximum likelihood estimator. So it says if I start with a distribution in this set curly PD, and I let P star denote its log concave projection distribution, the corresponding log concave projection distribution, if I have a perturbation, a delta, and it's such that when I take the log of the log concave projection, I add t times delta, if that function is concave for some sufficiently small t, then I have this inequality between integrals with respect to p and integrals with respect to p star. So as a special case of this result, if I take delta to be a concave function, then that's a concave plus a concave, so it's concave, so that's certainly a valid choice. And just flipping it over to a convex function, it's saying that there's a convex ordering between the P star, the projection, and the original distribution. Okay? What do I mean by this convex ordering? It means that expectations under P star of convex functions are bounded above by their expectations under the original distribution P. So specializing that further, if I took any linear function, then I could conclude that the mean of the projection distribution is the same as the mean of the original distribution. So when I fitted that log concave maximum likelihood estimator here, the mean of this fitted density would be exactly the same as a sample mean. Not close to, exactly the same as a sample mean. But for instance, I would be shrinking the second moment of the data. Okay, another very basic question you might want to ask is, in what sense do I need to be close to a distribution P in order for the corresponding log concave projections to be close? So really we're asking about the continuity properties of this projection. And somehow the right notion we need to kind of metrize the class curly PD and curly FD to do that. And the right notion of distance on the set curly PD is the L1 Wasserstein distance between two probability measures, which I can think of an infimum over all couplings xy, where x has got distribution p, y has got my distribution q of the expected Euclidean distance between x and y. Okay. And the result then says that this log concave projection, when I metrize the space curly PD with this L1 Wasserstein distance, and I metrize curly FD with the Wasserstein distance, this is continuous. So that's kind of nice, but unfortunately it's not uniformly continuous. And maybe that doesn't come as such a surprise because, you know, I have to have the convex hull of the data or the distribution is not supported on a hyperplane. So if I got my distribution closer and closer to being supported on a hyperplane, you could easily imagine that kind of modulus of continuity is going to blow up here. And indeed that is the case, and it took me about 10 years to come up with a more quantitative version of this, continuity result. And so what we're doing here is we're introducing a quantity that is telling you sort of how close are you to being concentrated on a hyperplane. It's like a robust form of a minimum eigenvalue. It's based on a first moment rather than a second moment. So once you've subtracted the mean here, you're thinking about projecting the data into one dimension and asking about the expected value of the absolute value of that distance. And then you're taking an infimum over all unit directional unit vectors in the unit Euclidean sphere here to give you some notion of how close you are to being concentrated on a hyperplane. And what we can prove is that if you're in the set curly PD, then this quantity epsilon p is positive. That's perhaps not too much of a surprise. But now the Hellinger distance, so this is a related notion of distance to the total variation distance. The Hellinger distance between the log concave projections of two different distributions is bounded above by this quantity here, the L1 Wasserstein distance raised to the power a quarter, and then divided by this maximum of epsilon p and epsilon q. So this is a local Holder continuity result, right, with exponent 1/4, and we can prove that this 1/4 is optimal. In some ways, that's disappointing that you can't get a larger exponent here because it's sort of saying that the worst case convergence rate in the empirical case could potentially be quite slow. But let me return now to the well-specified case. So a kind of core problem was how fast can you estimate this log concave density? So this was something I worked on for a long time, and this was a key result that ended up being really quite a surprise to the community. So again, we're looking at, now we're working with the squared Hellinger's distance. It could have worked with other distances, but this is a very natural one here. We take the worst case risk. Now notice that I don't need to kind of restrict the class of log concave densities. I don't need to worry about the height or the volume of the convex hull or anything like that. This is over the whole class of log concave densities. And the minimax lower bound here, so this is only a lower bound for now, behaves like n to the minus 4/5 in one dimension compared with, well, this is on a squared error scale, so it should be like n to the minus 2/3 in the Grenander case. We're getting its faster rate of n to the minus 4/5 in one dimension. But we're getting this very surprising rate of n to the minus 2 over d plus 1 when d is greater than or equal to 2. So many experts had believed that the rate should be n to the minus 4 over d plus 4 in all dimensions here. Notice that 2 over d plus 1 is the same as 4 over d plus 4 in 2 dimensions, right? So this is a different rate when d is greater than or equal to 3, and it's a slower rate. So the intuition for thinking that it should be 4 over d plus 4 comes from thinking that concave functions are twice differentiable almost everywhere, and that concavity or convexity can be characterized in terms of the positive definiteness or negative definiteness of the Hessian matrix. So essentially, concavity is like a second derivative condition, and so people would have expected the same rate as if you had densities with two bounded derivatives, for instance. But what we're seeing is that the problem is fundamentally harder than that, and the reason is that even though these densities are twice differentiable almost everywhere, it's a set of measure 0 that's screwing you here. So, for instance, uniform distributions on convex compact sets are log concave, but they can be very badly behaved on the boundary of their support. They can be discontinuous. And it's really estimating the support of the density that's what's driving the rate in the higher dimensions, not estimating the density in the bulk. So that was a kind of very interesting and surprising conclusion. Well, how close do we get when we use the log concave maximum likelihood estimator? Oh, yeah. So it was proved also that this constant can be taken independent of d. With the maximum likelihood estimator, so I'm actually going to strengthen the kind of notion of distance. I'm going to work with a larger notion of distance. So here we're looking at the log ratio of the estimate to the truth. This is very like a Kullback-Leibler divergence. It's just that I'm taking the average with respect to the empirical distribution rather than with respect to the Fn hat density. And there's a natural inequality that you can prove. It's rather special to the log concave MLE because in general this quantity needn't be non-negative, but it is for the log concave MLE, and it's actually majorizes the Kullback-Leibler divergence, and that in turn majorizes the squared Hellinger distance. So I'm getting an upper bound on a larger quantity, and what we were able to prove is that log concave MLE attains exactly the same rate up to a universal constant as we saw before in one dimension, and the same rate up to a log factor in 2 and 3 dimensions. And then later on, at least in this smaller distance, the squared Hellinger distance, Kerr et al. Were able to show that this estimator achieves this n to the minus 2 over d plus 1 up to this log factor when d is greater than or equal to 4. Okay, so actually I should emphasize that what we're seeing here is a cursive dimensionality, this n to the minus 2 over d plus 1. The bigger the dimension, the slower the rate of convergence, and really this is quite a severe cursive dimensionality. For instance, so if I thought about d being 9, for instance, I've got n to the minus 1/5 on a squared error scale. That's saying something like I'd need 10 to the 10 observations to do roughly as well as I would in a well-specified parametric model with 100 observations, right? So that's a very severe form of cursive dimensionality that really means that the log concave MLE is only a realistic estimator in relatively low dimensional situations. Certainly 1, 2, 3 dimensions, maybe 4, but probably not really beyond that. And then there's the computational issue, which itself gets more and more challenging in higher dimensions. So I do want to be thinking of this in relatively low dimensional situations. There are ways in which one can add further structure to the class to try to do better in higher dimensions, but that's not something I'm going to go into today. Okay, so that was the story for the kind of worst case estimation rate for the log concave maximum likelihood estimator. It presents a reasonably coherent, complete story. But we took a worst case, a supremum over all log concave densities here, and that might be unduly pessimistic in some cases. So we might ask the question, are there some densities that we might be able to estimate at a faster rate? I wouldn't have asked this question if the answer was going to be no. So what sort of densities might we be able to estimate faster? Well, let's go back to the structure of the MLE. We have this tent structure to the log concave MLE on the log scale. And what you might think to yourself is that if the true density were of this tent structure form, particularly with a small number of affine pieces, then we might be able to do better than this worst case rate. Okay? And that is indeed the case. So, in fact, in the very simplest case, where you've just got one affine piece in the unidimensional univariate case, what we're able to prove, and I find this a very intriguing result, is that the log concave MLE is attaining actually a parametric rate of convergence, no log factor here, a parametric rate of convergence in total variation distance. So, because the log concave MLE, I didn't tell it was from the data was coming from a uniform density, right? And yet it's doing as well in terms of rate as if I told you in advance that the data came from a uniform density. That's a very powerful form of adaptation. More generally, let us write curly f superscript k for the class of univariate log concave densities for which log k is k affine. So these densities are log k affine. Hopefully that's relatively clear what that means. It just means there are k affine pieces on the log scale. And here is a result that I would call a sharp oracle inequality. So to try to unpack what this result is saying, let's first of all simplify to the situation where the density is not just a log concave density, but actually belongs to this curly fk class. In that case, I can take this second term to be 0. Right? And what this is saying is that the expected dx squared distance is behaving like k over n up to this logarithmic factor. So if k is relatively small, and I ignore the log factor, then this, because this is like a squared distance, this is a parametric rate of convergence. Of course, there is a log factor penalty that I wouldn't normally get in a parametric case. But that's really, again, I think quite a nice form of adaptation. And more generally, this is what I call a sharp oracle inequality, because even if I'm not exactly from one of these curly fk classes, but I'm only close to it, then I just have to add on this approximation error term. And what's intriguing about this is that the kind of constant in front of this approximation error term is 1, and that's why I call it a sharp oracle inequality. That's the best you could hope for here. Okay, so we talked about the log concave MLE being supported on the convex hull of the data. That's fine in many applications, but you might kind of not like this ridge structure, or you might want a smooth density estimate. You think to yourself, well, if I want to smooth, then what have I gained? Because I've got to choose this tuning parameter of how much to smooth. But it turns out there's a very natural way to do the smoothing, and again, a fully automatic way, and that is to convolve the log concave MLE with a Gaussian density centered at the origin. Of course, I've got to choose the covariance matrix, and I choose the covariance matrix to be the difference between the sample covariance matrix and the covariance matrix corresponding to the original log concave MLE. So why does this make any sense? Well, because I've got a log concave density convolved with a log concave distribution, so it's still log concave. Because it's centered at 0, I'm not changing the mean compared with this, and that exactly agreed with the sample mean. But my choice of the A hat here means that I'm now matching exactly the first 2 moments of the data, right? Because the covariance matrix is the original covariance matrix of this guy plus this A hat, but I chose that to be the difference between these two things, so I'm getting back the original sample covariance matrix. But convolving is a smoothing operation, so I'm now ending up with a real analytic density that's supported on the whole of R to the D. So this is a picture of what this looks like. We've got the log concave MLE in red, which is estimating this dotted density. And the green is just doing a little bit of smoothing here that kind of smooths out the rough edges and makes it supported on the whole of R to the D. And this is a corresponding plot on the log scale. And you can see that the way that the tails enter here. Okay, so I'm not sure if there is anyone here who would consider themselves an information theorist. Good, okay. So this is a slide for you. One of the key quantities in information theory is the notion of entropy. The Shannon entropy, h of f, is just minus the integral of f log f. This is a key quantity in information theory. People like to think about entropy maximizing distributions. So for instance, the Gaussian density maximizes entropy amongst all distributions on the real line with a fixed scale, fixed variance constraint. The exponential density maximizes entropy amongst all densities supported on the non-negative half line, again with a mean constraint. So these are rather sort of central object in information theory. And here's a result that I find very intriguing. I asked the question, if you give me a distribution in curly PD, how do I maximize entropy, but now subject to a convex ordering constraint? So I've been a bit sloppy in my notation because I've got a density on the left and a distribution on the right, but hopefully it's clear what I mean. I'm talking about the distribution with that density when I say this. So I'm trying to maximize the entropy over all densities F for which the corresponding distribution is convex bounded by P. And the answer is, it's a log concave projection of P, right? So, you know, I think your flabber should be gasted at this point. Why is that? Because I haven't said anything about log concavity in asking this question. And yet this log concave projection is coming out very naturally here. So I find this an intriguing result. Okay, how am I doing for time? Okay, so in the last kind of 15 minutes or so of this talk, I'd like to talk about a kind of very recent application of some of these ideas that I've been working on with three fantastic collaborators. Oliver Feng, who was my PhD student postdoc, is now at University of Bath, moving to London School of Economics. Min Xu is at Rutgers University, and Yu Chen was Min's PhD student. So I want to think about a very simple linear regression problem. So this is low-dimensional linear regression. I often give this talk under the title, How Should We Do Linear Regression? Let's say I don't know how to do that. I might turn to my collaborator, Lucy, and say, Lucy, how should you do linear regression? And Lucy would say, aha, yeah, you should use ordinary least squares, okay? But what if I were to be really annoying and say, well, how do I know that this is the best you can do? Then Lucy would quickly come back and say, aha. So again, what we teach our undergraduates is to use the Gauss-Markov theorem, right? So I want to revisit the Gauss-Markov theorem. So the setting is that we have a standard linear model here where our errors have a density F0. And I want to claim that actually we can often do better than to just rely on the Gauss-Markov theorem, because the Gauss-Markov theorem says that the ordinary squares estimator has minimal covariance among all linear unbiased estimators. But that restriction to linear unbiased estimators is a very severe one. And we can often do better by working with potentially biased and nonlinear estimators. And in particular, I'm going to focus on what I'll call the class of M estimators. So that is, for a general differentiable loss function, an estimator of this form, and the least squares estimator just takes sort of L of Z to be Z squared, or Z squared over 2, right? If L is differentiable, then any minimizer, any optimizer of that problem satisfies what I call these Z estimating equations. So the sort of things that I have in mind here, well, you've got the least squares estimator, which corresponds to taking this L to be this dotted line here. You could think of the least absolute deviation estimator, where you just take the L1 loss, but you could also sort of interpolate between these with the famous robust Huber loss functions. So these are quadratic around the origin, but then they have a transition point, this k. Notice that that's a k that the user has to choose. That's a kind of a bit annoying that they have to choose it, but then you're growing linearly after that, and the aim is that this linear growth should be dampening down the effect of the outliers. What do we know about M estimators? So under some regularity conditions, we can argue that this M estimator converges to the true beta 0 at rate root n, and that the asymptotic variance factorizes into a term that depends on the original covariate and a term that depends on the choice of loss function, or equivalently its negative derivative psi. This guy here is a matrix, but this is a scalar, which I'll call the asymptotic variance factor, and it's got a rather simple form here. So to go back to our simple example of ordinary least squares, where L of z is z squared over 2, that means psi of z minus z, and the asymptotic variance factor in that case is just the second moment of the error distribution. Okay, so that's a rather simple case. But what I want to do is to think about what's the optimal loss function. Okay, when I haven't necessarily got Gaussian errors, I'm going to define the score function to be the derivative of the log density and the Fisher information, which I can define as the integral of the square of the derivative of the density divided by the density. We know what the solution is here. The solution is to take L to be minus the log of the true error density, which corresponds to taking the MLE, and then the asymptotic variance factor is just 1 over the Fisher information. Okay, this is matching the Cramer-Rao lower bound, for those of you who've done a course in parametric statistics. That seems like the problem solved, but the issue is here that you need to know the true error density in order to use it. That's one issue. The second issue is a computational one. So if I try to do this with a Cauchy density, I end up with this very cuspy type of landscape that's very hard to optimize. So to simplify that situation, I'm going to restrict my attention to convex loss functions L, which means that the corresponding psi function, the negative derivative L, is what I call antitonic. So for the purposes of here, being antitonic doesn't mean that you're some kind of gin addict. It just means that you're decreasing. It's the opposite of being isotonic, right? In that case, the oracle maximum likelihood estimator is a convex M estimator if and only if the original density is log concave. So we're seeing log concavity coming back here. But I'm actually going to be particularly interested in the case where this true density is not log concave, and I'll ask the question, what's the statistical price, if any, that I pay for the computational convenience of working with this convex loss function? And what we know about convexity is that any local minimizer is then a global minimizer, and it's very straightforward then to compute these convex M estimators. And it turns out that trying to find the psi function that optimizes that minimizes the asymptotic variance of the beta hat amounts to projecting the density onto this class of log concave densities, but not with respect to Kullback-Leibler divergence, now with respect to a different notion of divergence called the Fisher divergence. And the solution can be obtained using a very modern idea called score matching. So this is at the heart of diffusion models, for those of you who know something about modern machine learning, which is how people do generative modeling these days. Okay, so I want to explain the solution to this score matching problem. I'll explain it in the context of an example, but this is actually the general solution. The example is going to be a Cauchy density. That's a very long way from being log concave. It doesn't even have a finite mean, of course. So we wouldn't have Kullback-Leibler projection, but we still do have a notion of Fisher divergence projection. First of all, we compute what I call the density quantile function. That's a composition of the density with the quantile function. That's got a relatively simple formula for the Cauchy density. And you can prove that the Cauchy density quantile function, or that you can prove that a density quantile function is concave if and only if the original density is log concave. Okay? So Cauchy is not log concave, so we don't get a convex function, a concave function, we get this green curve here. But then I can compute its least concave majorand, that's what's in blue there, and then I can compute its derivative. And so my claim is that this turns out to be the best decreasing approximation to this score function, which is in green, okay, with respect to L2P0 projection, which is the right notion of projection for our purposes. And then when we have some data, we can try to estimate this antitonic score projection. We end up with something like this red curve here, which is doing, as hopefully I can convince you, a reasonably good job. So there's much more that I could say about that, but I'm running out of time, so I won't say more on that for now, because I'm sure people would like to know a little bit about the future and some open problems. I'll talk. I think I've got one problem that I'd regard as a sort of computational question, and then a few theoretical questions that I think are interesting. So the computational question is related to computing the log concave MLE, which I think remains a really interesting question. But what I think is a particular nice twist on this is how can we compute the log concave MLE fast? If you add or delete a point, I want to be able to do this faster than just starting from scratch again, right? At the moment, I don't know any way apart from to start from scratch, which is definitely not ideal. Right, so I introduced the smooth log concave maximum likelihood estimator. I would like to know something about how that estimator performs. I think that would be intriguing. The boundary behavior of log concave MLE. So we know that it's supported on the convex hull of the data. Shape constraint estimators often exhibit sort of quite extreme behavior around the boundary. I would like to know something about that. In particular, I can say some things in the case of a uniform distribution on 0, 1, but not as much as I'd like to be able to say. And then, for instance, how can I try to estimate a log concave density if some of the data have missing components? So the simplest form of this example would be, let's say I've got bivariate data, and sometimes I observe a star or an A where I don't see a particular coordinate. You might ask, can I use the kind of univariate observations where I only have one coordinate available to do better than just throwing those data points away? So an extreme version of this would be to actually say, let's suppose I know the marginal distributions of the log concave density. How does that help me estimate the bivariate density? Okay, so those are a few open problems. Okay, let me wrap up and say that so the log concave maximum likelihood estimator provides what I think is a very attractive non-parametric density estimator because it's fully automatic. You've got none of these irksome bandwidths to choose. We are able to prove that it attains the minimax optimal rate of convergence, at least up to a logarithmic factor in 2 or more dimensions. And it can adapt. I think this is an intriguing property of a lot of shape-constrained estimators, that it's able to estimate subclasses of densities faster than the worst case, even in multivariate settings, although I didn't talk about that. And the particular subclass of interest here is a class of densities for which the log density is close to being k-affine. One of the reasons I particularly like this area is there are a lot of intriguing connections with other areas, so with information theory, with distributional orderings, from the last part of the talk with robust statistics and score matching, so lots of connections with other areas, some of which are still under investigation. And I kind of really like the way that now we're seeing that shape constraints are being moved from kind of classic problems in say, density estimation or regression, non-parametric regression, into kind of really core practical problems, things that practitioners want to do every day, like linear regression, and giving better ways of being able to do linear regression. So if you're interested, particularly in the last part of the talk, then there's an archive preprint available. But with that, I'll stop there. Thank you very much for your attention.
Thank you very much for the very nice talk. Any questions from the audience?
Yeah, thank you for wonderful talk. So I have maybe a couple of questions. First, for the k-affine, you have upper bound. Mm-hmm. So do we know the lower bound if you restrict to be in that class?
Right.
So you have log term there, right?
I don't know about the optimality of the log term, okay. but I do know that even if you told me that the density was log k affine, and even if you told me the locations of the breakpoints, then I could only get k over n, right?
Right, so, that's expected.
So I definitely couldn't beat it. I don't know about whether this log term is necessary.
Still not clear yet. Okay. Yeah. Second question is that in regression, people put a lot of effort, making sparsity assumption. So in the case of density estimation, what would be similar thoughts?
Yeah, so that's a really good question. And so there are two ways in which I've tried to incorporate further structure into log concave densities to be able to do it in high dimensions.
Yeah.
One is through a notion of independent component analysis. So that would be where you think of observing data that are a linear transformation of a random vector with independent components. Okay. And so the independent components sort of act like an additive model would in a regression function. But you've got this linear transformation, so it's more like a kind of index model, right? And we showed how there's a notion of projection onto the class of log concave ICA densities, the one where you have this ICA structure as well as log concave components. And that notion of projection, really interestingly, preserves the mixing matrix or the unmixing matrix, the linear transformation matrix, which is typically the thing that you're particularly interested in. So that's really intriguing because that means there's a certain sense in which you can, without loss of generality, assume that your components have a log concave density here. The other way that you might think about doing it, that works even in really high dimensions, is to think of having what you might call homothetic superlevel sets. So you might say, I've got the same shape for the superlevel sets, just on different scales as I move out. So spherical symmetry would be the simplest form, elliptical symmetry, but for a general convex body, you could think of these sort of antithetic superlevel sets, and then you've kind of reduced the problem to a univariate problem. You've just got to estimate the kind of the radial function here. And that's another way in which you can try and deal with a high-dimensional case.
Yeah. Maybe a third question. So you focus on log concave. So what other shape constraints turn out to be also important and interesting?
I would say that log concave, certainly in the d-dimensional case, is like the central one. Yeah. One can generalize this or shrink the class to what's called the class of S-concave densities. So that's where instead of the logarithm being concave, you have like the density or the log density to a power involving the S being concave. That allows you to go beyond having exponential tails to like polynomial tails. If you work with the wider class, it doesn't retain all the nice properties of log concavity, though. For instance, if you take log convolutions of S1 and an S concave, sorry, S1 concave and an S2 concave, then their convolution is S concave, where S is the harmonic mean of S1 and S2. It's not, quite as nice as the original class.
Thank you very much.
Pleasure. There's a question at the back. I have an R package. There are two relevant R packages. One is called log conc dead, which is for computing the log concave MLE in d dimensions. There's a faster one in one dimension that's not due to me called log con dens. But there's also an R package called ASM. So you have an ASMR package due to the warm tingly feeling you get when you use it. Which we use for computing linear regression estimators. That's the last part of the talk. Yeah. It depends on what the truth is. If the truth has this log k affine form, then yes, it can be better. It's also true that the worst case does correspond to densities that have discontinuities on the boundary of the convex hull. But even for kind of regular densities and something like estimating a Gaussian density, you're going to get a rate of n to the minus 4 over d plus 4. So you will still see a cursor dimensionality there. So estimating log concave densities is hard both statistically and computationally. So you can do a little bit better than the worst case sometimes, but there will still typically be a cursive dimensionality present. You should expect that in non-parametric problems. No, I don't think so. Yeah, I think you would still see, even for mean squared error, you'd still see a cursive dimensionality effect. Yeah.
Oh, okay, thank you. Let's just thank you, Professor Richard Samworth again. And let's have a break.